Hello everyone, Barev Bolorin. Всем привет. My name is Yuri Barseghyan, and I will be talking today about infrastructure as code with Terraform. Briefly about myself, I'm a cloud architect and consultant with 20 years of diverse IT experience. My journey began with web software development, where I gained some experience with some multiple programming languages and frameworks, Scala, Java, and some others. And then I slowly shifted towards the cloud. And over the past 8 years, it has been focused mainly on cloud, big data, and data platforms. During this time, I have primarily worked with AWS, not so much. I mean, in the beginning, then I shifted towards last 5 years, mainly working in Azure, specializing in services such as Kubernetes, Databricks, Terraform, and many others. So during this session, you will learn about cloud migration. Then we will explore cloud orchestration, cloud infrastructure orchestration, and dive into Terraform and hopefully you will receive some valuable tips and tricks. So let's begin by discussing cloud migration. So cloud migration is a process of transferring digital assets, such as data, workloads, IT resources, applications to cloud infrastructure. And migration may involve all or only specific assets. So you can, for example, start migrating or duplicating your data assets to the cloud, and organizations can benefit from starting to establish cloud data platforms that can support use cases such as data science, research, machine learning, data-driven applications, business intelligence, reporting, and many others. So now let's concentrate on data platform specifically. In a cloud data platform, multiple subscriptions are typically utilized, and each subscription often comprises one or more virtual networks. So to establish connectivity between these virtual networks and an on-premise network, the most common approach is to use hub-and-spoke network topology. And additionally, and this slides specifically for Azure, just because I'm mainly on Azure. But you can do same stuff with AWS and many other cloud providers as well. So additionally, within each subscription, there will be some numerous resources such as virtual machines, Kubernetes clusters, databases, storages. And the number of resources can range from tens to hundreds or even thousands, depending on the size of your cloud platform. And this complexity highlights the need for a proper cloud infrastructure orchestration. Without it, you will be lost. So let's now delve into the topic of cloud infrastructure orchestration. And let's check what is it actually. So orchestration serves to address the requirements of automating the lifecycle of cloud infrastructure. And this includes tasks such as provisioning, updating, and destroying the infrastructure components. And let's explore the available options for that. So we got manual option, or UI. Then we got programmatic version of it that you can code with some programming language or script it. Then we have options that are cloud provider specific, infrastructure as code. And then we have some open source infrastructure as code options. So we will be checking each of them. So manual orchestration involves using a web-based user interface to create and manage cloud resources. Here is an example for Azure. It's like Visual-based, that you will be going step by step and configuring your resource in a UI. So this option primarily excels in providing a convenient interface for viewing resources and accessing subscription settings and billing information, mostly like view-based. But manual orchestration lacks the efficiency, scalability, and repeatability provided by more advanced orchestration options. And as Jared Short well said, you would be hard-pressed to find someone managing anything of scale who thinks letting folks point and click in the console is the optimal route, and I completely agree with it. And while manual orchestration can be useful for certain tasks or initial setups, it's typically not the preferred method for managing complex and scalable cloud infrastructures. So let's check the programmatic. For the programmatic approach, there are several options available. We got CLI, or command line interface. We got the REST API. And then we have a cloud provider specific SDKs. So let's explore each of them individually. For the programmatic CLI, the command line tools provided by cloud providers, and they enable automation and scripting of infrastructure management tasks. And they allow you to execute commands and perform actions programmatically or within the scripts. And here we got an example. This provided command is using, I don't know if you can see, yeah, it's visible. Provided command is using the Azure CLI to create an Azure Kubernetes service. Cluster with various configuration options. So you have multiple options, zone redundancy, naming, and so on and so on. Quite many options like available, and you really need to know how to configure it properly, of course. Then the other one is the REST API. So CLI itself will make calls to the REST API and to perform actions that each of CLI commands support. But however, there are those rare times when you need to call REST API that isn't supported by CLI. In those cases, you will use the REST API call directly. And here is an example for the previous use case for the CLI, but with the REST call, where you have a REST HTTP put request to create or update, say, managed Azure Kubernetes service cluster. So you got the put call up on the top and the body that represents the configuration for your Azure Kubernetes service itself. Then we got programmatic cloud service provider specific. So if you want to orchestrate your infrastructure as part of your software, or if you require more programmatic control and customization, using SDK is a good option or better option. SDKs provide libraries and APIs that allow you to interact with a cloud provider services directly from your code. And here is an example of Python. So this provided code demonstrates how to use Azure SDK for Python to create or update managed Azure Kubernetes service cluster. So we got like 3 options. Yeah, it's pretty small because there is a lot of code. That's why you don't want to use this. So, and let's discuss some shortcomings. So let's review the challenges associated with programmatic approach. So a programmatic approach is inherently imperative in nature. So imperative scripts tend to be more complex and harder to maintain, especially as the infrastructure grows in size and complexity. Then each change or update requires modifying the script or your program and potentially leads to errors or inconsistencies. And with an imperative approach, the burden of managing the infrastructure lies on the script. As a result, the script must account for all possible scenarios, handle error conditions, and ensure proper sequencing of steps. So imperative scripting can be useful for ad hoc queries and like repetitive operational tasks, where the focus is on performing specific static actions, but it's not well suited for orchestrating complex cloud infrastructure when the emphasis is on managing the overall infrastructure and its interdependencies. So yes, we went through those. So now cloud providers offer their own infrastructure as code tools that are specific to their platform. For example, AWS got the CloudFormation CDK, and Azure has ARM templates and Bicep. So using cloud provider-specific infrastructure as code tools is a good choice if you are exclusively working with a single provider and focusing on creating and configuring resources specific to that provider. So these tools are designed to seamlessly integrate with the services, so it's a very good option. One advantage of using cloud provider-specific infrastructure as code tools is that they usually provide support for new features shortly after their release. And this ensures that you can leverage those latest capabilities straight when they are released. And as a comparison between those like options for every single cloud provider, when comparing the different options, like there are the JSON-based options, that's ARM template in Azure and CloudFormation in AWS. They are often considered cumbersome and difficult to read because you have huge configuration files and JSON is not like so much human readable. And on the other hand, tools like CDK and Bicep offer a more developer-friendly approach to infrastructure as code. They allow you to write code using familiar programming languages and provide higher level of abstraction that simplify infrastructure provisioning and configuration. So, and the last but not least is the open source infrastructure as code tools. Among those, the most popular ones are Terraform and Pulumi. And Terraform and Pulumi provides multi-cloud support, while Bicep and CDK are tailored more for specific cloud environments. So let's check the comparison. Let's provide a brief comparison of those tools specifically for Azure. So the Pulumi is like, they call it code native, because basically it's like the main approach is it allows writing your infrastructure as a software with familiar programming languages like TypeScript, JSON, JavaScript, Python, Go, C#, and others. Then we got the Bicep. It's focused providing a simplified and more expressive way to define Azure resources. And it's a DSL over the old good ARM templates, and it's Azure-centric again. But one reason why you would use this, if you are exclusively on Azure, is because it provides you backward compatibility and straight out of the box compatibility with ARM templates. So you can use, if you have a lot of ARM templates already existing from back, I don't know, 2010 or something, then you can utilize here, import them, and actually continue working within in Bicep itself. And with Terraform, so it consists actually of two parts. It has its own DSL. That's the main, that's original kind of DSL called its own language, HCL. And they provide also Terraform CDK, which is similar to the Pulumi, so you can use programming languages supported. But the problem with, and it's supposed to be interoperable between the HCL, and because it's using the state management and so on is the same, but it's still experimental, and the APIs might break and so on. So maybe for the production use cases, it's not really recommended at this point, at least. So yeah, here is a table where like you can see some comparison between them. So let's dive deeper into Terraform specifically. Terraform is open source infrastructure. It's called this from the website, so you can maybe read it, but it's like gives you consistent CLI workflow and manages hundreds of cloud services. So it's a good option if you have multi-cloud use cases, or actually even if you need to manage something on-prem. Main philosophy is that you write the infrastructure as code using their language, HCL, which is called HashiCorp configuration language. Then you run Terraform plan to check whether your execution plan for the configuration that you provided matches or like matches your expectations of what's supposed to be deployed to the cloud, and then you apply those changes that it will take your code, and it will kind of try to do everything to reach the desired state of the configuration. So it's out of your hands. It's a declarative way of defining the infrastructure. So you don't need to take care of any problems if anything happens in the cloud. It's kind of on the platform, on the framework itself. Terraform will take care of it, or that's the promise. Then let's check the providers. The providers are modules responsible for managing interactions with specific upstream APIs, and they are acting as the bridge between Terraform and those various cloud providers. They are providers for public clouds, AWS, Azure, GCP, IBM even, and that IBM, what was it? The first presentation about IBM services, those are available also. You can actually configure them using Terraform as well. So for the open source tools also there are providers for Kubernetes and Helm chart if you are using those for your Kubernetes deployments, Databricks and so on. And that's maybe the main purpose why you would choose Terraform over, even if you are actually, like mostly you will start maybe Azure specific or like AWS specific, but if you will be using any open source frameworks like Kubernetes, Databricks and others, I'm pretty sure you will end up like in a situation there when you would like actually to include that configuration of those services to be part of your infrastructure code. And Terraform provides that out of the box with the providers. And then there are providers for popular SaaS services, Auth0, Artifactory, and so on. In total, there are around 3,200 providers. It's growing all the time. Last time I was giving this talk, like a year ago, there were only like 2,100 maybe providers available. Then let's talk about Terraform state. Terraform maintains the state of infrastructure it manages in a dedicated state file. It's typically called Terraform TF state and is stored by default locally. It has a custom format, JSON format, that maps the Terraform resources defined in your configuration files to their real-world representation. Oops, sorry. And yeah, and Terraform uses the state file. It's a very crucial component to reference, like it creates execution plans and compares what you are trying to do with what it has in the state and what's the reality also in the on your cloud part. And based on it, it will provide you the plan of execution and what's going to happen actually. So it's kind of a very crucial component of Terraform itself. So let's take a look into some Terraform code. I didn't know that I can show you a demo, so I just have a code on the screen. So let's just go through it. So let's start from the top. There is, hopefully you can read it, yes. So first Terraform block that it specifies the required providers for the configuration. And in this case, required provider is Azure RM provider. From the source, you define the source and the version that you want to use. Then the provider blocks after it configures the providers that you have. So for each chosen provider that's required by your configuration, you can configure that provider specifically. And within the configuration block, provider block, you can specify like additional settings such as authentication details towards the cloud provider and some default configuration and features to enable or disable. So customize it for your own needs. And then after that starts actually the Terraform code itself. You start defining your infrastructure. So we start from the Azure RM resource group resource that will create a resource group where the resources will be. It's like a folder where resources will be created, and we specify location. So you just define like what's the name of it, where do you want to create it, and so on. Next comes network security group that's utilized under virtual networks, and last is the virtual network itself, configuration for it, where you define actually the name of your virtual network, same location, the address prefix, and there we create 2 subnets. And the last subnet, as you can see, is referencing the security group that we created or defined earlier. So you can kind of like put like point to the resources created earlier, reference them, and use them dynamically as you would do like with any programming language itself. So that's the code. And yeah, the main commands to remember, like command line interface commands to remember is this Terraform init, Terraform plan, and Terraform apply, where the init will just initialize and download all the specified providers that are specified under required providers block. And let's check the rest of the commands. Then we got Terraform plan. So if we execute Terraform plan for the code that we have, then we will get this type of output. And it provides you an overview of the changes that will be made to your infrastructure when you apply the Terraform configuration. So it performs like dry run to show you what actions Terraform will take without actually making any changes. The Terraform plan command is useful for previewing the impact of your changes before applying them, and it helps you to validate your Terraform configuration and ensures that it aligns with your expectations. So here you will see that we will have like 3 resources that will be created. There are no changes and nothing gets destroyed because it's a completely new environment. We don't have anything and we are creating first time those resources. And here is the state file, an example of state file generated like after the apply, when you will run apply. And it contains also some metadata, such as like that's in the beginning, what's the Terraform version in use, some serial number, lineage, and some outputs if you specify any. Then we can update the resource. So for example, we can add a security rule to our network security group. So that's the security rule block within the code that we didn't have before. And if we try to run the plan, then you will see the following output. And the output indicates that Terraform will make modifications to the existing network security group, and it will add the new security rule, and no resources will be added or destroyed in this operation. You see that there is 0 to add in the bottom, 1 to change, and 0 to destroy. So then let's take a look into resource graph actually. That's quite important, and that's in the core of the Terraform, how it works. So Terraform uses a resource graph to represent the dependencies between resources in the infrastructure, and it analyzes the configuration files and constructs a direct acyclic graph of resources, allowing Terraform to understand the order in which resources need to be created, updated, and destroyed. And based on it, it can also identify the resources that are independent and can perform and run them simultaneously, so in parallel. And that's a very nice feature that it figures out it's for you, and it's like accelerates and does the work very fast. So like that's really is a very helpful feature, and that's all based on resource graph feature. And you can preview, you can visualize it as well to understand your infrastructure if you want. And now let's explore some tips and tricks that can make your life easier with Terraform. At least they made mine. For improved isolation and greater simplification and better access control, consider separating configuration files for different environments, for your pro, dev, and so on. Then you will have less dependencies between them, and you can kind of work independently. And the rest of the tricks will help you actually with, because this has its own issues if you just take this independently and just apply these rules, but the rest of the tips will help you actually to not end up in the trouble. So isolate groups of infrastructure with different life cycles into separate state files. So you break the monolithic configuration where everything of your cloud platform is defined in one big Terraform file, and everything everything saved in one state file, because if it will become gigantic, then if you run Terraform plan, it will take you like half an hour or 1 hour to just plan the stuff to see what you are actually gonna get as a result of your change. So this also minimizes the blast radius of changes. If something goes wrong, it will affect only the pieces that are within that state file itself. And it improved the Terraform plan performance, as I mentioned already earlier. And then define and use modules. And modules, they provide a higher level of abstraction, simplify configuration, and promote code reuse. And shared modules save time across projects by reducing, replacing, and ensuring consistent deployment. Those are very, very helpful. And if you can start early with them, that's a very good option, because otherwise it can be a bit hard to start introducing them like later on. But it's like possible, of course, and many go that way. So stability and security, related log Terraform modules and provider versions. Those are quite important. That you will get always the same consistent output. Store state files in a shared encrypted storage. It enhances collaboration and enables treating the state file as a critical piece of infrastructure. So, which means also that you need to enable backups, versioning, least privilege access control, and auditing logging for your state file, because state file will contain a lot of secrets, everything what you generate within the platform. So it's a crucial component. Like, it's not just important for Terraform itself, but also it has a lot of secrets and things that you don't want that will get leaked or exposed. I think we don't have time for questions, so questions let's leave for later, and I welcome you or invite to my workshop that will be held in the workroom 113W and will be between 2 and 3 o'clock. Thank you very much.